Okay, well, my computer's acting up, which is just a little disheartening, after given us some of the history I've had with it. All right, so here's homework number 11, problem 2. We have this tree right here, and the Hartford Facilities crew are doing some forestry cleanup in the woods near the campus with the aid of a come-along. If you don't know what a come-along is, you can Google that. What a come-along is. It's like a little ratchety kind of linear winch type of thing with some chain and that kind of thing. It's kind of cool. And this tree weighs 2,400 pounds, and it's been cut with a felling notch, which is this little guy down here, that makes the resisting moment at here negligible. That is, it's just supporting the vertical and horizontal, but not a moment. At the moment, the tree is, at this moment, the tree is leaning at 6 degrees over here to the left, while the rope makes an angle of about 15 degrees with the horizontal, and is attached to at LAG right here, 5 feet above the center of gravity, which is 13 feet above the notch. The tree has been topped at 8 feet above where the rope is attached. And by the way, you don't actually need to know that. We want to find the amount of tension caused by the come-along winch, and we also want the reaction forces at O right here. So this is a pretty good problem, I think, in terms of trying to make this into like a real thing. Okay, so here is page 2, and I will fill out all the other things that I ask you to fill out, like your name, in this case, my name. Oh, I forgot the semester is spring of 2021. Sure. ES110, and this is homework 11. Problem 2. Well, there's a number of things going on right here, so let me try to make a good drawing of this thing right here. So there you go, we're on a slope here. This is going to be, I'll draw faintly, here's my tree coming up here. So we have a tree, it's got a little notch going on there, and he comes up to like there and right there. Oh, I didn't draw him at an angle, which I should have, and I meant to. I might even exaggerate some of the angles. So let me draw the vertical here. Let me draw what the tree is doing here. And there's the notch, which we're going to call O. Sure. And in terms of the lengths, right here is the center of gravity. Right here is where the thing is attached, and then right here is the top of the thing, and there is where we're going to attach that. I really made this exaggerated compared to the original one right there, and so that like here is horizontal, and that's going to be theta. I'll say what that dimension is here in a minute. This is going to be, we call it G. This is going to be A. This is B up here. This angle, let me draw in the line that it forms with right in there, is going to be beta. We can draw what that is later. I'll say this is L AB. This is LAG, and this is LOG, which spells log. Isn't that hilarious? I didn't do that on purpose. I swear to you. But it's a lot funnier now that you saw it out loud, right? That spells log. Hilarious. And this is point C. Here you go. Here's the winch. For some reason I put an M next to it. I don't know why. We'll go given. And things we want to know. Let's see, the weight of the whole thing is going to be 2,400 pounds. Gotcha. Beta is equal to 6 degrees. I'll even write it over here. Beta 6 degrees, theta is 15 degrees. LAG is 5 feet. So that right there, it's just 5 feet, right? So we've attached the rope 5 feet higher than like the middle of the log, basically, of the thing. And LOG is equal to 13 feet. Now, I gave you that LAB was equal to 8 feet. So if you do this math, I think it actually makes it like so the thing is uniform. But it didn't have to be uniform. If you see the original picture of the thing, just keep in mind it could taper, right? So just because it's a log, it doesn't mean that the center of gravity is in the center of the height of the thing, but it is in this case. You can see it kind of gets narrow at the top in the picture, but that's okay. I decided that it didn't get narrow at the top, and that it was all good. So we want to find the tension in the come along. I suppose he's come along M, as far as I'm writing there. I don't know why I put M in there. And then reaction. And noting that this does not support a moment. So we write out our FBD. And I can tell you that probably the best thing to do is to exaggerate some of the angles in such a way so that you can get the dimensions in there so that they'll make sense. Right there. This is to the center. And then this up here is a little bit higher. And then right here, and I didn't give you a dimension. And by the way, when you're making these, I suggest if you look and you see a direction that something has to be, like there's no doubt, just go ahead and make it in that direction. Right there, right? I saw this tension was going in that direction. In the horizontal direction, the reaction right there has to be to the left. So I decided that's going to be ROX, and this is ROY. This is the weight, and this is the force of the tension. Some of the dimensions we might want to have in here, and these are a little trickier. Let's see. Oops, I just kind of messed this up. There you go. That right there is going to be 6 degrees. Right? We're in agreement. I could put this one right here. This is going to be 15 degrees. So when we go to the sum, and I could put these other dimensions in here, they're just going to kind of get in the way a little bit. Right? That you say this is LAG, so that's going to be 5 feet. And I can't write this over here without getting in the way of a lot of other things. So I'll go a little bit crazy. It ain't pretty, but it'll communicate. That's more important. There's 13 feet right there. Right? So here's what we'll do. Some of the moments about O, counterclockwise is positive, and we take a look here. First off, I want to go with this force right here. I'm going to say that I want to make sure I know that that's 6 degrees. I'm going to say he's going to be clockwise, therefore negative, force of the tension times the cosine of 6 plus 15, or 21 degrees, right? And then the distance that it's going to be is going to be 5 plus 13. You see how that works? Right? Here we got the component of this thing. It has two components. One is going down and towards the point about which we're taking the moment. So it's only going to be the cosine of that 21 degrees of that force. And here's the moment arm that's perpendicular to that component. We have another one right here, and that is definitely going to be the opposite, obviously. But this guy right here is actually going to be the sine of 6 degrees, right? Because it's going to be the opposite of this angle. That's going to be the thing that's perpendicular to this 13 feet, right? So that's going to be the weight right here of 2,400 pounds, sine of 6, and times 13 equals 0. So we get a tension in this cable that's necessary, right? 2,400, 6 degrees times the sine, 13 feet. But now we're going to divide by 18 feet and divide by the cosine of 21. So we get, in order to be able to support this thing, we have 194.1 pounds. You want to find the reactions, sum of the forces in the y direction. We could have done the x direction first. Didn't matter. We'll set it up as positive. We'll go Roy. Roy is positive because he's going up. We're going to get negative of 2,400 because that's the weight. But we're also going to get pulling this down of 194.1. And now in the y direction right here, you got to be careful. That's going to be the sine of 15. So 2,400, and that's going to be, whoa, that should be negative 2. It's also pulling down. Almost made a mistake. Really easy to make them. Add them together, 2,450 pounds. And that's coming downwards, right? And the sum of the forces in the x direction is equal to 0. There you go, there's positive right there. All we got is ROX, he's in a negative direction, plus my FT, which is 194.1, and that's going to be the cosine of 15 degrees. So we got our ROX, and we write 194.1, 15 times cos, there you go, cosine, we get 187.5 pounds, and so the reaction's right there. Let's go back to the original and find out what they just said the reaction forces. It didn't say the magnitude and direction, so we're totally okay just to answer it as a vector, but with the magnitudes and directions. I guess it's the vectors, if you would. But you totally could, if it was asked the way that maybe I would intended, but I forgot to write it out that way, that you can write it with a magnitude and direction, right, and with a quadrant. So maybe I'll go ahead and do that right here. I'll say that the RO is the square root of 2450 squared plus 187.5 squared, right? square root. So it doesn't change all that much from the vertical one. 2,457 pounds. The angle of the reaction, the RO right there, is the inverse tangent. And the vertical is 2,450. The horizontal is 187.5. So we have 2,450, 187.5 divided inverse tangent, and we get that's going to be 85.62 degrees. Right? So the answer to this one, let me write these back, is that it's going to be 194.1 pounds. Oops, I made that look like a 1 and the L are the same thing. And that's going to be in tension. And B, I'm going to write that R is going to be equal to, where did we go right here? Negative 187.5 I plus negative 2,450 pounds J LB, or R is equal to 2,457 pounds at 85.62 degrees. So either one of those is a totally acceptable answer for what's taking place right there at the notch where this thing is about to go tumbling down. The end. Hopefully this thing will end a lot better than the last one did. Oh, there you go. It looks like it's going to work.